So this discussion is standing waves, and we'll start with standing waves on a string fixed at both ends. So this would be like a guitar string or a violin string or something like that. And it turns out you get what you get with this when you want standing waves, which you might have seen in some of the demos we did a second ago, a little in the previous videos. You can get a standing wave that looks like this, like that, and so if I was to really, so this is basically half a wave. The full wave, again, this is the end of the string, and this is the end of the string. A full wavelength would go all the way out and then come back up again, right? That would be a full wavelength. And so if the length between the two anchoring points is L, the actual wavelength for this mode is lambda equals 2L. In other words, I would have to have another L here before I got a full wavelength in. This is half a wavelength, right? Here's a full wavelength of a wave, and what we have here is this much of it. And so this is called the fundamental mode, or the first harmonic. Or the fundamental. I'll try to use the names harmonics. Musicians we'll talk about these things. So, but you can get other modes on a string. The next one you'll get looks like this. And I've tried to demonstrate it with the vibrating string. Here, you've actually got a full wavelength, right? You've got the wavelength of the wave is equal to the distance between the 2 points, or the wavelength is equal to L. The next harmonic looks like this. Again, the string is always in the same 2 points, but now we have 3 loops. Again, so the string is now vibrating like this, right, up and down, but with 3. These are called loops. And so on, right? These guys are called nodes. In this case, I get 3 lambda over 2, that is 1.5 lambdas is equal to L, or lambda is equal to 2L over 3. Right. Notice I could write this one as equal to 2L over 2, and if I do that, you start seeing a pattern, right? I can write this as, lambda equals 2L is 2L over 1, then the next one is 2L over 2, and the next one is 2L over 3. And you can probably guess that when it's got 4 loops in there, it's 2L over 4, and so on. And so this tells you what the allowed wavelengths are for standing waves on a string, right? So lambda sub n, in other words, the first one is 2L over 1. Lambda sub 2, the second one, the second harmonic is 2L over 2. The third harmonic, lambda sub 3, is 2L over 3, and so on. Right? This is just 2L over 1, 2L over 2, 2L over 3, like that. Those are all the possible standing waves you can get on a string. So what about the frequency? If you remember our formula, lambda is equal to, the velocity is equal to the wavelength times the frequency. Well, if that means that the frequency is equal to the velocity over the wavelength, or the nth frequency is equal to the velocity over the nth wavelength, right? the velocity is the same for everybody. All the waves travel the same speed on the string. All the sound waves, regardless of their wavelength or frequency, travel the same speed in air. All the light waves, regardless of their frequency, travel the same speed in any given material, but in particular in a vacuum or in air. And so if we want to know what the frequencies are, well, we can say this is V over 2L over N, because that's what lambda sub n is, right? And that means the nth harmonic is equal to NV over 2L, right? But so F1 is just V over 2L. You follow that? So here's the frequency of the nth harmonic. It's just the velocity of the wave divided by the wavelength of the nth harmonic. That just comes from our standard velocity relationship between the wavelength and the frequency. And then if you just plug in what the wavelength of the nth harmonic is in terms of the length of the string, you get this formula. You put the n in the numerator since it was in the denominator of the denominator, and you get this formula like this. And then you say, well, if you stick in 1 here, this is the frequency of the first harmonic. But what that means is f sub n is equal to n f sub 1, because nv over 2l, v over 2l is just f1. And so the frequency of the nth harmonic is n times the frequency of the first harmonic, right? And so you know if your guitar string plays a middle C, then it can also play the harmonics. So if f sub 1 is 262 hertz, right? Then f2 is equal to, I've got to do this in my head, 524, and then f sub 3 is equal to 786, and then f sub 4 is equal to 1048. Did I do that right? 786 looks reasonable. These are all in hertz. And so that means a guitar string that can play this for a fundamental can also play these guys, because there's standing waves on that string also. When you pluck, in fact, when you pluck a string, a guitar string or a violin string, the string will play fundamental and a bunch of these other ones depending on how it's plucked and what kind of instrument it is. It's the reason that when stringed instruments are all playing a middle C, they don't all sound the same. A violin's middle C sounds different from a guitar's middle C, and so on. It's because they're mixing in different harmonics and at different volumes. And so it's also why a synthesizer is so good at playing a variety of instruments. You can make a keyboard synthesizer sound like a trumpet or a violin or a guitar or a tuba. It's because electronically they know, the people who built the synthesizer, the recipe of these harmonics for making the sound that makes a violin, or for making the sound that makes a tuba, or for making the sound that makes a guitar. And so they can just mix these harmonics just right, put the right recipe together, and now your instrument will sound like it's a guitar or a cello or something like that. So we're going to talk about standing waves in the tube open at both ends. We just did standing waves in the string. This is just like wind instruments, most wind instruments. So this would be like a clarinet or a saxophone or a trumpet or a tuba or a French horn, those types of things. And the standing waves you set up are kind of, in some ways, the opposite, but exactly the same as what you see in a stringed instrument. Here's my wind instrument. I'm just representing it as a single tube. And instead of having a node at both ends, like we did for the stringed instrument, you have what's called an antinode at both ends. And so the wave kind of looks like this. Instead of having a node, you have a peak. This is like if you took the stringed instrument shape, which looks like this, right? And you just flipped it, right? So that the nodes were in the middle and the antinode was on the outside. And so you have a vibration here, which maybe comes from your mouth or a reed or something like that. So it's kind of a loud here and a loud here as it comes out of the back. And you only get resonances for waves that are integer numbers of that fit in here the way they do on the strings, right? And so this is the first harmonic. I guess I'll write in blue. First harmonic, or the fundamental. And notice that again, since a full wave looks like this, right? A full wave looks like, I'll just draw it this way. Right? A full wave goes low to high to low to high. This just goes from here to here. That's what this wave is. And so it's half a wavelength. And so just like with the strings, lambda 1, the first harmonic, the wavelength of the first harmonic is equal to twice the length of the tube, right? Just like it was in the first one. And so then we can draw the second harmonic, which also plays on this tube, right? A little bigger than that, right? And this guy looks like this. Oh, I'm going to use a blue. Looks like this. And then it can, when it vibrates, it goes like this, right? And here, lambda 2 is equal to L because it goes from low to high, or high to low to high, or low to high to low. And so this is actually one full wave, right? It goes from peak to peak again, or trough to peak to trough again. And so this is starting to look very much like the string one we did a couple of videos ago. And so let me draw the last one here, right? And I'm probably going to get this one wrong because this one goes from high to low to high to low, like that. And this guy goes from low to high to low. I just kind of got it right. And notice this is 3 half wavelengths, and so this is a 2, right? Lambda 2 equals L. And here, just like with the case of the string, this is 3 halves, 1.5 wavelengths. There's a full wave, and these other two pieces are each a quarter, so it's a full wave and a half. So it's 3 over 2 lambda is equal to L, or lambda 3 is equal to 2L over 3. And once again, just like last time, you see the pattern. This is 2L over 1. This is, if we want to call this as 2L over 2. This is, let me get it right, 2L over 1. There we go. It's 2L over 2, 2L over 3. And so here, just like with the strings, we get lambda n is equal to 2L over n. And then if you calculate the frequencies the way we did last time, I won't go through the math again, it's exactly the same. We get the frequency of the nth harmonic is n times the frequency of the first harmonic. And so for a tube open at both ends, it's just like a string instrument. And these are the two relevant formulas. And so we're going to draw that this way. We're going to say, look, here's my tube. And this is like, there aren't too many instruments. The most common instrument you see for this is like the pop bottle. Have you ever blown on a pop bottle and you get a tone? It depends on how much water is in there, or how much pop is in there. And so so the waves in this, the standing waves, which determine what the tone is going to be, have a note at this end and an anti-note at this end, a peak at that end, and so it's going to look like that, and then that, and this is a quarter of a wavelength, right? Because a wave looks like this, but here I've just started at the node, which is this point, and I've gone to the peak, which is this point, and so that's a quarter of a wavelength. So if this length here is L, if the length of my tube is L, then I get the first harmonic, lambda 1, is 4 times the length of the tube, right? Because in order to get a full wavelength, I would have to have 3 more lengths of that tube, and so it's 4L. And so now I'm going to draw the next one, try to draw the same shape roughly, right? And this guy's going to have 2 nodes, and so he's going to look like this. I didn't do a very good job. Let me just try one more time. That's a little better. And then this guy's going to look like that. And so this is half a wavelength, and that's a quarter of a wavelength. And so so I can say 3/4, oops, 3/4 of the wavelength is equal to L, or lambda 2 is 4L over 3. The next one is going to look like this. It's going to have 2 of those nodes in it, and it's going to get harder and harder for me to draw. So I'm going to do 1, 2, 3. Not too bad. So that's a full wavelength, and that's a quarter of a wavelength, not drawn very well by me, but what are you going to do? And so in this case, I have this is a wave and a quarter, right? And so it's 5/4 times the wavelength is equal to the length of the tube, or L, or lambda 3. I'll write it in black here. Lambda 3 equals 4L over 5. And now you can start to see lambda 1 is equal to 4L, lambda 2 is equal to 4L over 3, lambda 3 is equal to 4L over 5, lambda n is equal to 4L over 2n minus 1. Something like that. That's our wavelength, and I'll determine the frequency here in just a second. So if we have the wavelength of the nth harmonic is 4L over 2n minus 1, then we can say, just like we did before, we can say, well, the velocity of the wave is equal to lambda n times Fn, or the frequency of the nth harmonic is the velocity over lambda n, which is equal to the velocity over this thing, right, which is 4L over 2n minus 1. And so Fn is equal to 2n minus 1 times v over 4L. If you stick in 1 there, you just get v over 4L. So F1 is equal to v over 4L. And so that means Fn is equal to 2n minus 1 times F1. And so if you know the first harmonic, you know the second harmonic is a 3, the third harmonic is a 5. And so sometimes people will write this way. They'll say F1 is equal to F1, F3 is equal to 3F1, F5 is equal to 5F1, and so on. So rather than numbering these 1, 2, and 3 and having them come out as 1, 3, and 5, they'll just say there is no second harmonic, there is no fourth harmonic, and so on.